And welcome to your last day of the lectures of the week. Our lecture of the day is Intro to Cross-Validation, Naive-Bayes Decision Tree Random Forest. And to give us a hand learning these topics, we have today with us Professor John Paisley, Associate Professor of Electrical Engineering and member of Data Science Institute of Columbia University. His specialties are Bayesian machine learning and deep learning applications. And just for curiosity, he also has a passion for drawing. Welcome, Professor John, to this cohort of DS4A Columbia.
Thank you. Can everybody hear me all right? The video should be okay. Thank you again for inviting me to give today's lectures. Let me go ahead and share my screen. And so you should be able to see see my screen, to see the Python, which says how do I build a prediction model for Lending Club loan defaults. It's the first lecture that we're going to be talking about in the next 2 hours or so. I also have on my second screen the Slack channel with the live chat. So I should be able to see some questions here. However, I have to lecture and then look at the live chat. So I'm sorry if I miss your question as they're going by. But I will be able to see when things are posted on the left. If anything is not clear, I'm happy to modify, to slow down or to go back and repeat some things. We should have plenty of time with 2 hours to get through this material. Okay, so again, thank you. And let's go ahead and get started with the first 2-hour lecture. So today, the way that I'm planning on doing this, I'm not sure how other lecturers have done it in past weeks. I'm sorry if it's a bit different or not, but I plan to, I'm assuming that it's going to be similar. I'm just going to go through the Python notebook, walk through each step along the way, add some of my own comments as they come to me. But I know from when you present something, when you have slides and you're also lecturing, that it's important that what you're saying and what you're seeing on the screen are not completely different things, because then you're fighting kind of who do you pay attention to. So I plan to read all the text in the Python notebook and then kind of maybe take breaks and add my own take on it, or my own views on what we're talking about. So let's go ahead and get started. Today, in the first lecture, we're going to be talking about how to build prediction models for Lending Club loan defaults. So this is going to be a classification problem where we have 2 classes. We'll talk about the data more as we go along, but I'll give my overview. Where we have information about people who applied for a loan, and then they either were able to pay their loan back in full, or they defaulted, which means that they couldn't pay it in full, and so the lender had to absorb that as a loss. And so the question, the classification problem we're interested in is, given a person's application information, what is the probability that they'll be able to pay back their loan? And that's ultimately what we care about. What is the likelihood they'll be able to pay back their loan? And then you can make decisions based off of that, whether you would actually give them the loan or not, based off of what you predict their payback likelihood to be. And so, of course, the way that we build these models is we have a lot of data of past instances, of past applications, and then the result of whether they paid their loan back or not. So that's the general classification problem in a nutshell. Now, the problem, of course, is how do we do that classification? So there are many different ways that you could make these decisions based off of data, whether to give the loan or not. And so we need to come up with some sort of a model that we can learn from the data. And then that model will contain the information about whether we give the loan to the next applicant in the future. So we're going to look at 3 models in this lecture at a high level. The goal is that by the end of this case that you'll be familiar with the naive Bayes classification model, the decision tree classification model, and the random forest classification model. And actually what we'll see is that the decision tree is very closely related to the random forest. Decision tree is one model, one tree, and the random forest is many trees combined together. So they're closely related. So really there are two key classification models plus one additional way of using a classification model called the random forest. Specifically, we're going to learn some of the theory behind both the classifiers, the naive Bayes classifier and the decision tree classifier, the structure of them, some of the underlying math to give you a sense of what they're doing, and also how we can use cross-validation in order to choose which model to pick. And so, of course, I looked ahead in preparation, and I know that it's not going to be a clear winner which model is the best in this data set. And that's often going to be the case, that they all kind of perform similarly good. But the process is important. Learning how to first be able to assess how each model will do is crucial. That's what cross-validation does. And also being able to evaluate which model you prefer. Even if it turns out that they all perform similarly, you need to learn that information. So the process is really the key thing in how we're going to evaluate these models. So during this case study, we're also going to create a baseline classifier using logistic regression, which I believe you've already seen before. That's going to be the baseline that we're going to compare with to see if we get any improvement or not. We'll then introduce the naive Bayes classifier. That'll be a section talking about naive Bayes, which is a type of a classifier. It's a general framework, but we'll see it for this particular data set. And then we'll move on to decision trees and random forest classifiers, which are kind of the second part is decision trees and random forest classifiers. You can think of them as being combined together. And that's going to be, in our goal to try to beat this baseline of the logistic regression model. We're going to see if these can improve. We'll then go on to implement these, pick the best model quantitatively, and then quantify how and pick the best model quantitatively. And of course, being able to quantify the choice of the model is important for us to know so that we can justify why we're making the decisions we're making. We can make a reasoned argument for why we pick one model over the other. So the introduction to the problem, the business context is we've seen in previous case, what we can do to determine if one aspect of personal information is important when predicting default status. So for example, whether the income information is verified or not, we can see how that can help us predict whether somebody will default on their loan. This type of analysis helps with simplifying the lending process. However, the biggest question for every peer-to-peer lending company, which is whether or not the user will default, is still not answered from the previous case. The algorithm to predict default probability is the core of the business case that we care about, and we need to build it carefully. So we need to build a model that will predict whether somebody will pay back their loan or not. So to summarize the business problem in a sentence, the task at hand is to build a classification model for determining whether a particular user will default on their loan or not. To wrap up the introduction, some analytical context. So as a data scientist, you now need to focus on honing the classification algorithm. I'm not sure if you saw logistic regression before or not, but we really care, I believe you did before, but we really care now about focusing on building classifiers. There are many different choices that you can make on how to do a classification, and kind of being aware of the main techniques and some of their advantages and disadvantages is important. So we need to verify quantitatively based on data that the algorithm is going to work for future data. So how do we do that? If we build a model on past data, how can we be confident that it will work with future data? In addition, we need to expand our toolkit to not rely solely on logistic regression, as it has some shortcomings that are better handled by other types of models. The final classification algorithm will then be selected via the model evaluation procedures that have been introduced in previous cases. We'll consider models generated from logistic regression. So we're gonna go back and relearn a logistic regression model on this data set, as well as two new algorithms that we're going to actually discuss in some detail. So we won't review what logistic regression is, but we will discuss naive Bayes classifiers and random forests in some detail. The case is structured as follows. First, we're going to generate a baseline model from the logistic regression algorithm. We're then going to, and we're going to see, what the performance looks like. We're then going to introduce the naive Bayes classifier and the random forest classifier. We're going to talk about them kind of at a high level, what they do and what they're all about. Then we're going to use these algorithms to try to upgrade our model, to try to improve upon logistic regression. And spoiler alert, we're not really going to be able to improve that much because the data set's pretty simple. But that the important thing is, this is the process. And for a different data set, it often does happen that you get some improvement. And then finally, we're going to use the cross-validation technique to select the best model that we want to use. Okay, so I think this should already all been run. So if you have this separately, you can run this as well. We're importing everything. We're kind of getting all of the packages all set up here and reading in the data with this block of code to read in the Lending Club data set. You can see here we're reading it in. And now we're showing the 5 first data points in the data set. I don't know, it sounds like you maybe have seen this data set before, but I'll quickly refresh your memories about what's in this data set. So it's tabular data. Each row of the table is one data point in the data set, or one observation in the data set. The first column, as it's structured in the file, the first column is what we want to predict. It's the label. So it's whether the loan has been fully paid or not. So this is all past information. So we know the answer to each of these. So you see in the first 5 data points, we have 4 of them where the loans were fully paid off. So that's a good thing. And in one of them, they charged off, which means that they didn't pay the full loan. Maybe they paid part of it, but they didn't pay the full loan. And so they had to default. And so the company that gave the loan had to absorb that as a loss. So that's called charged off. We then have the set of covariates that are going to allow us to help us to predict what's going to happen. So this first column is the output we want to predict. The remaining columns are the information that we have to go off of in order to make that prediction. So we have, I don't believe we're going to end up using all of this, but you could use all of it if it's helpful. We have annual income. So this is the income of the person who is receiving the loan. We have verification status, verified, source verified, or not verified. If I remember correctly, because I think I have seen the previous case, that means whether or not that their income was actually proven, because so this might not be true, but they self-report their income and then you check whether they're true, that's truly their income or not. Perhaps by showing a tax document or something like that. So this is the verification status. There are 3 of them. Empirical length, I actually don't remember what that is. Home ownership, whether they own or rent their home. The interest rate of their loan, that's an important one. How much interest are they paying on their loan? The loan amount, this is how much they're asking for. The purpose of the loan, so what are they asking for the loan for? You can see, for example, it's a credit card, or it's a car, or they want a loan for their small business or others. So there are many different options that you could pick for the purpose. Oh, okay, employment length, yeah. So how long have they been employed? I see I think empirical. Maybe that's the data scientist in me. So the purpose, and then how long they selected to pay back their loan. They could apparently either pay back their loan in 36 months, or they could pay back their loan in 60 months. So either 3 years to pay it back or 5 years to pay it back. And then grade is C. I can't remember exactly what that is, but the grade is also a bit of information. The grade is I said C, it's some sort of a digit, a number, a letter. Okay, credit scoring, yeah, thank you. Okay, so before we proceed, let's review the results in the code from the final model that we used in the previous case. So we're running, this is our data, we're running the logistic regression model. It's all been pre-run on my computer. So we optimized the model, we learned the parameters. It only took 7 iterations to learn because it's not a very complicated data set. And the function value is the objective function. So it's just something you're trying to optimize, I assume minimize this function value. Okay, so now after we run that, we get some variables as output. We get, for example, predict with VS contains the probabilities calculated by the logistic model. So what that is for each of the data points that we're learning the model on, we then learn a probability from the model of whether they will pay it back or not. So the probability is the probability is whether they will pay it back. So that's what the probability indicates. So 1 minus that probability tells you whether the probability that they will not pay it back. And so we get that output for each data point in our model, from our model. Here, as I said, the values closer to 1 correspond to users that are more likely to fully pay back their debt. And in order to visualize this a little better, we've created a scatter plot that we'll see below of users given their loan amount and their annual income and showing the probability of paying it back. So this is the scatter plot code. I'll describe it rather than read it so you can see the scatter plot. So we've run the model in this block. We've gotten our probabilities, and now we're visualizing the results, some of the results of the training in these scatter plots. So we have 2 scatter plots. We have really 4 things that we can show. We can separate the data set into all the people who paid back their loans. That's one data set. And then a separate partition of the data into all the people who did not pay back their loans. So we take our training data and partition into 2 groups, those who successfully paid back their loans and those who didn't. So here we see on the left, this is all the data of people who paid back their loans. This is the people who did not pay back their loans. That's how we're choosing to visualize it. On the x-axis, what we're showing is the loan amount. So this is not of course, the raw number. This is, we've taken the features and we've scaled them. So we've standardized them. I think I'll talk about this more a bit later. So the loan amount originally went from a low to a high number. Now that's been scaled to be in this interval. So there's a mapping from 0 to the actual loan amount. So this is the range of the values for the loan amount. More negative is a smaller loan amount, more positive is a higher loan amount. And the y-axis is the log of the annual income then standardized. So this is related to their income. The more negative is a lower income, the more positive is a higher income. That's this for all the people who paid off their loans and all the people who did not pay off their loans. So here, first thing you can notice is that the x-axes relate to each other. The y-axis isn't exactly the same. So here we go from -4, which is right there, up to +2, which is about right there. So it's not identical, but I guess there's quite a bit of overlap. So you can kind of look back and forth. So why are there negative values on the y-axis? So the annual income is first, the log is taken, then the mean is subtracted. And then there might be a division by a number as well, but the mean is subtracted, that's why. So the average should be close to 0. So the average between these two should be 0. So if you kind of overlapped this data with this data, then the overall average should be 0. You can see here that there, whether that's the case or not, I don't know. Okay, so what you can see here is the yellow is the probability of paying it back. The blue, more yellow is higher probability that they pay it back. More blue is higher probability that they don't pay it back. You can kind of eyeball this. It's not, so this is a nice plot with something you can conclude from it, but it's not necessarily obvious from this plot. One thing is that it looks a bit more yellow here than here. You would have to quantify that, I suppose, to be confident. But it looks like we're more confident about the true positives, that we're actually catching those, and the true negatives we're more catching those. Let's see, what else is there that we can say? So as the loan amount gets smaller, it looks like the yellow is kind of more to the left, which means that people who borrow less have an easier time paying it back than people who borrow more. That makes sense. It looks like as their income goes up, the yellow is kind of the bluer, the more negative, maybe perhaps the more blue, the more positive, the more yellow. It's not clear or obvious, but slightly that way, which makes sense as well, that the more a person makes, the easier time they're going to have paying back the loans. So you would expect to see the yellow more in the upper left, because they're borrowing less and they're earning more income. Those people should have an easier time paying back their loan. And as you go lower to the right, they're borrowing more and earning less income. Those people should perhaps have a harder time paying back their loan. So that's some initial data analysis, just kind of exploratory data analysis. We can also, so it's exploratory data analysis based off of the results of the logistic regression model, because the yellow and the blue is not in the original data. The yellow and the blue is the result of what the logistic regression model thinks is happening. We can also now quantify this with the ROC curve and the AUC of that ROC curve to see, in general, the probability of performance. So that's what this chunk of code is doing. It's showing, it's taking all the predictions from the logistic regression model and then plotting its performance as an ROC curve. And so I believe you've seen this before, but to refresh your memories, the ROC curve, the x-axis is the false positive rate. So that means among all the data points in your data set that were classified as 0, that was a negative. So in this case, negative means they don't pay back their loan. Positive means they do pay back their loan. Among all the data points that in the data set that are negative, what fraction are you declaring as a positive? That's a false positive. And the true positives are among all the data points in your data set that are actually a positive. What fraction of those are you correctly classifying as a positive? That's the true positive. So the reason that you can have multiple values is you need a threshold to make a decision. So we probably will see, I think we'll see this later, but it's good to review it now. So when you get a probability from your logistic regression model that the person will pay back their loan, how do you make a decision to give them the loan or not? You have to make a decision. Are you going to give them the loan based off this probability? So the easiest, simplest thing is to just give them the loan if they have more than a 50% chance of paying it back. So if the probability comes back 0.6 that they will pay back their loan, you say, okay, they're more likely to pay back their loan according to my model than to not pay back my loan, so I'll give them a loan. However, of course, in real life, if you're only getting paid, if you're a lender and you're only getting paid back 60% of the time, that's going to destroy your business most likely. Right? So if somebody only has a 60% chance of paying back their loan, according to your model, even though it's more likely that they pay it back than not, there's perhaps too much risk in giving them a loan, so you might not want to. So perhaps you would increase that to say 80% chance or 90% chance. So you would, if somebody has less than, say, a 90% chance that they're going to pay back their loan, according to your model, you might not want to give them the loan, even though they still do have a better chance of paying back than not. So that's a decision that is beyond the scope of the model. That's what the human and that's the policy of the company and so on. That's but there is a parameter that you get to choose. So for example, if you're basically that parameter is from 0 to 1 of the probability whether they're going to pay back the loan. So for example, what this ROC curve is doing is saying, sweep the parameter from 0 to 1 and then see what the performance is. So for example, if you set it to 0, that means that anybody who has a probability of paying back their loan greater than 0, you're going to give them the loan. So of course you're going to get all of the true positives, all the people who can pay back their loan, you're going to give them the loan. So that's going to be 1. However, you're also going to have a lot of false positives because everybody in your data set who didn't end up paying back their loan, you're also going to give them the loan because their probability, according to your model, will be greater than 0, kind of by definition. So you're going to have false positive of 1 and also true positive of 1. You're literally giving everybody the loan. And so you catch everybody who is good, but you also, unfortunately, everybody who ends up not paying back their loan, you falsely say that they're going to pay it back. And then as you sweep from 0 to 1, you can imagine that once you go to 1 in the other extreme, you're not giving the loan to anybody because the model is not going to give a probability of 1, most likely. It'll give a little bit less than 1 for everybody. And so you're not giving the loan to anybody, which means you get no false positives, but you also get no true positives. You give the loan to nobody. And then in between is these numbers. So for example, for a particular value of the parameter that you probability of paying back, a particular threshold, you get a false positive of 40%. So 40% of the bad loans you end up giving the loan to. That's not good. But for that particular threshold, you also catch about 65% or 70% of the true positives. So that's, I'm sorry if this is all review from a previous case, but that's what the ROC is giving you. These are for basically for the threshold, this is the sweep of your performance. The blue dotted line is like the worst case scenario. It's random guessing. If you just flipped a coin and randomly guessed, that you would get this blue dotted line. So you have to be above the blue dotted line, otherwise something's definitely wrong. And ultimately, what you want is this orange line to be as much to the upper left as possible, because that means you're catching everybody who's good and not incorrectly catching people who are bad, according to the data set, before it eventually goes to 1, 1. So it has to start at 0, 0, has to end at 1, 1, and then at some point along the way, it's going to be a curve like this. So that's the ROC curve. And then the AUC is simply, the ROC is an entire function. You can't really give a number with it. You can give a function, a plot. If you want to take this entire function and boil it down to one number, that's the AUC, the area under this curve. So we go from 0 to 1 in the x-axis and 0 to 1 in the right y-axis. Therefore, the area of that square is 1. We want, and the area under the curve is the area, what is the area of this white space here? So basically everything below the orange line, what's that area? So it's got to be something less than 1. And the more this orange line goes to the upper left, the more area is going to be underneath it. And that's what the AUC is. So 0.69 is not a probability. The meaning of 0.69 here is not like a probability of your performance or something like that. you think it's a probability because it's between 0 and 1, but it's not a probability. It's an area underneath this curve. You want that to be as large as possible, and that'll just give you a number that you can use to compare ROC curves, ROC curves. Okay, so how do we know if we're overfitting the model? So that's kind of review, some kind of setting the stage. Now let's look into questioning whether or not we're overfitting the model, and that's going to allow us to discuss the cross-validation technique that I also think you saw before. So in order to know whether we're overfitting the model, we can't just look at the training data. We can't build a model on our data set and then look at how that model performs on the data that you use to learn it. Because that could leave, so ROC is this function, AUC is this area under the function. So you calculate the AUC from the ROC. So they're kind of two different ways of thinking about the same thing. If somebody says, what's the ROC, you have to give a picture. The way I think of it is, if somebody says, what's the ROC, you can only answer them by showing them a picture. If somebody says, what's the AUC, you answer them by giving a number. But they're both calculated from the same exact thing. Okay, so how do we know if we're overfitting? How do we know if the model is doing really well on the training data, but once we get future data, it's going to do very poorly because the future data, because it's overfit. So the way that we do this in the first exercise is we're going to generate a 10-fold cross-validation ROC curve and then calculate the average AUC. So it's one way that we're going to show it. So if you remember what 10-fold cross-validation is, what I've been talking about so far is we have our entire data set. We then build the logistic regression model on that entire data set. And then we calculate the performance based off of how well that model does on the data that it was trained on. So we say, okay, so for a particular data point, that data point helped the model learn its parameters. And then we're going to try to see how well do those parameters predict that particular data point. So there's kind of two directions there. Cross-validation says take your data set and split it into 10 equally sized pieces at random. So if you have 1,000 data points, you're going to split your data set into 10 groups of 100, and each group it's random. How the data is partitioned into those two groups is totally random. We're then going to train our model on 9 of those groups and then use that model to try to predict the data in the 10th group. So the data that's being used to train the model is not the same as the data that you're then trying to predict to get performance of that model. So of course there are, if you have, there are 10 different ways that you can do this. If you're having a group of 9 and then a 10th group, there are 10 different ways you can make that group of 9. And there are 10 different ways that you can have that 10th group to predict. And so that's why you call it 10-fold cross-validation. You do this 10 different times, where each time you take one of the groups, one of the 10 groups, hold it out, train a brand new model on the 9 remaining groups, and then predict the 10th group. So we're going to actually learn 10 different models. It's the same model, it's the same logistic regression model, but the parameters that we learn are based off of 10 different groupings. And then to get the performance of how well our model is doing, we're going to get 10 different performances, one for each group. We can then, for each group, we get, just like before, we get a performance. We can then get an ROC curve for that group. And so we get 10 different ROC curves, one for each group, and 10 different AUCs, one for each group. And then we can average them and calculate, variance to show uncertainty in order to get the final performance. So the whole purpose of this, of cross-validation, as I think you've seen before, is that the data that you're predicting, that you're evaluating the quality of your model on, was not used to learn the model. And we assume that that's going to be a good representation of how things will be in the future, because we think, because of course, in practice, we're going to learn our model and then predict it on data in the future that we didn't see to learn the model. Right? So the data that we'll predict in the future was not used to learn the model. And so as long as things statistically have the same properties, the data that we have compared with the data we'll see in the future, as long as they have the same statistical properties, we can be confident that the performance on our held out data set, 1/10 of the data, will mimic the performance on the future data that we're going to see in the future. Okay, so we do this. We get the values TPRS. Let's see, so we use the function CVROC. We get TPRS, AUCS, and mean FPR. So what TPRS, okay, so I'm pretty sure that the answer to your question is, so TPRS stands for true positive rate. This CVROC curve, it's a built-in function, I believe. What it does is there's a lot going on in this algorithm actually that, you know, we can't talk about today, and how it does it. It's not super complicated or anything, but it's specific. As you know, when you work with this stuff, you know, you run into problems that you didn't anticipate in advance. So what it does is, for every false positive rate, every value along this axis, you get a value along this axis. What the CVROC curve does is it partitions this axis into an equally numbered set. So however many it does, I'm not sure, maybe 1,000 different points equally spaced here. And then it gives you the corresponding value in the y-axis. So TPRS is the set of values along the y-axis for each different point in the x-axis. Kind of implied is that you know what those values are on the x-axis. They're equally spaced, right? So the way that you can, if you wanted to plot this figure, you would take TPRS as the y-axis, and then you would, for the x-axis, you would evenly space those points from between 0 and 1. So if you get 1,000 points in TPRS, you take 1 over 1,000, 2 over 1,000, you take 1 over 1,000 and plot the first value, 2 over 1,000, plot the second value, 3 over 1,000, plot the third value, and so on between 0 and 1. So with cross-validation, how can you know it's not overfitting the model? The idea is that the whole concept of overfitting is that the model that you learn does really well on the data that it's trained on, because it learns all the idiosyncrasies of that data set. So it learns all the unique properties of that particular data set, and so it's able to predict very well. But those idiosyncrasies, usually they're called noise, just the noise in the data, don't translate to future data. Future data will not have the same little idiosyncrasies that the past data has. But that's okay, because that information is just noise. It's not actually important for predicting. So for example, if you think in terms of images, it's very easy to think. If you have images and you want to know if there's a tree in the image, if all of your training data has the tree in the upper left part of the image, and none of them in the upper right part of the image, if you were overfitting your model would say, focus on the upper left part of the image and try to see if there's a tree there, right? Just because every single data, this isn't a realistic situation, you would make sure your data set doesn't look like this. But if every single data point in your data set has the tree is in the upper left, or if it doesn't have the tree, then there's no tree. If the model overfits, the way to think of it is, it says, okay, I figured out that the tree is always in the upper left, so focus on that part of the image. and then learn to see if there's a tree there or not. But of course, in future data, the tree might be in the upper right part of the image. The model has overfit because it has found some idiosyncrasy within your training data that's not realistic about how the data really looks like. In this case, the idiosyncrasy is that it just so happens that in all the data points, the tree is in the upper left. Whereas in future data, you might get trees in the upper right. So that's the best I could do, kind of thinking up randomly. So that's the idea of overfitting. So with cross-validation, we want to make sure that the prediction on future data is not going to, that the training that you perform does not do something like that. And so the way that you can do that is by holding out data points that are not used to learn the model and see how well it does. Okay, so we run this, we get one answer below, and let me see, I guess I might need to speed up a bit. So we run all of this, we get our results, and here's what we see at the end of the day. Here's what we see. So the blue dotted line is the same as before. This is just random guessing. So it's kind of like the baseline. You have to be above this blue line, otherwise there's something definitely wrong. The red dotted line is the previous line that we saw before. That was how well, that was the ROC curve calculated based off of the training data only. The orange line is the average of the 10 different ROC curves that you got using cross-validation. So it's a different procedure. The model is the same, the algorithm you're using to learn the model is the same, the way that you calculate the ROC curve is the same, but the procedure is different. In the orange line, you have 10 different groups and you're calculating 10 different ROC curves. And you're learning the model on 9 groups, calculating the ROC curve on the 10th group, and then doing that 10 different times and averaging. So it's a different procedure to do the same exact thing. And what you see is the performance is a little bit worse. So if the performance is better of the orange, that's unusual, because the red line has all of the information in the model that's being then used to calculate the red line. Whereas the orange line, the information that you use to learn the model is not the same as the information that you're predicting based off of. So you don't expect to have an improved performance with cross-validation, but you do expect it to be more realistic of how the model will actually perform. And the goal is to get these two things to kind of be as close as possible, because that means that the data set doesn't have an overfitting problem. And so we see that here. The AUC 0.69 on the red curve. On the orange curve, the average AUC is 0.68, so it's a little bit worse, plus or minus 0.04. That's the uncertainty, because we have 10 different AUCs. And so we can calculate the mean of those 10 AUCs and the standard deviation of those 10 AUCs. And so we get uncertainty here. So if we have an overfitting problem, will the random guessing, so actually overfitting, overfitting would give you more to the upper left, because it means that you're doing really, really well on your training data, but that doesn't represent your testing data. So the orange curve should be closer, the cross-validated curve should be closer to the blue, or between the blue and the red. The more overfitting is being done, the closer the orange curve will be to the blue, the cross-validated curve. So the more overfitting, like I said, the more overfitting you have in the red curve, the closer the orange curve will be to the blue, which means that you didn't actually learn anything in the red curve. You just completely modeled the noise in the data, which is very rare. I mean, that doesn't happen a lot, but that's the concept. Okay, so we can see the average AUC is a bit smaller. The difference is small, indicating that there's not a big overfitting problem. Although the logistic regression, okay, so we've kind of evaluated logistic regression. Let's now move on to the meat of today, which is the 2 new classifiers we want to introduce. So although logistic regression is one of the most commonly used classification algorithms. It's not the only one. There's a large number of classifiers that you can pick from. Some of them are very standard, very famous. Naive Bayes and decision trees are the two that we're going to talk about. Those are very standard. Some of them are very unique to a specific problem that you're looking at. But you can almost think of it as like a toolkit that you get to pick from. Each classifier has its advantages and its disadvantages. For example, if you wanted to classify very complicated high-dimensional data like images, a logistic regression classifier would be way too simple and it would fail. But a neural network, which we're not talking about today, would be much more likely to succeed. So there are many different classifiers. Today we're going to talk about two: the naive Bayes classifier, which is a general framework for doing classification, and then the decision tree, which is another kind of general, well, not as general, because the decisions you need to make are a little bit fewer. Okay, so I think, I'm sorry, I see some questions, but I should move on to, because this is the new content. Okay, so let's first talk about the naive Bayes classifier. The classifier we're going to see next is based on a very simple but powerful result in statistics, which is Bayes' theorem. So before we can talk about how we use Bayes' theorem to classify data, we need to review what Bayes' theorem is, review notions of conditional probability, and so on. However, the idea of how this classifier works is pretty simple. So given a client with certain characteristics, given an application with certain information on it, we're going to use Bayes' theorem to learn how we can estimate the probability that that client will either default or not. And the way that we do that is by saying, does this person statistically look like my previous defaulters, or does this person look more like my previous non-defaulters? How does this person's application look like, compare with all the people in the past who were paid off their loans? And how does it compare with all the people who didn't pay off their loans? Whichever one it looks more similar to, we use that information to help us predict whether they'll pay their loan back or not, and then make a decision. And so the way that we do that, so it's similar with logistic regression, where we had a new applicant and we calculated the probability that they would pay their loan back or not. So in that situation, we calculated the probability that you'll pay your loan back given the information on your application. So it's the probability of the result given the input that you're giving me. So that's a probability. Bayes' rule flips that. So that's the key trick for Bayes classifiers. It flips that by using Bayes' rules. So maybe I'll talk about it more generally with A's and B's, and then I'll fill in kind of some information as we go along. So let A and B be two different events, a pair of events. So for example, A could be the event of a person pays back their loan, yes or no. And B could be the event of the information in their loan application. The conditional probability of the event A given B is the probability that you observe A given the information in B that has happened. So we write this as probability of A given B, or in shorthand, we put A bar B, so probability of this given this. And I believe you've seen this before. That can be written as the probability of A and B together divided by the probability of B alone. That's the conditional probability divided by the marginal probability, I'm sorry, the joint probability divided by the marginal probability produces the conditional. So this is A comma B divided by B. So in our situation, this is the probability that somebody, if we just focus, so we have a lot of information about their application. If we just let B be whether they're verified or not, to make it simple, if we just focused on that, we could calculate the probability that they default given that their income is verified. Right, that would be a conditional probability. That would be the proportion or the fraction of all the defaulters, just focusing on those whose income has been verified. So if we went to our entire data set, we would pick out all the data points that have been verified and then calculate the probability of defaulting based only on that data. That's mathematically what this is saying mathematically. Of course, there's nothing special about A or B. So we say P of A given B is P of A comma B divided by P of B. We could flip that and say P of B given A is P of B and A divided by P of A. Mathematically, it's the same thing. There's no difference. However, Bayes' rule kind of pops out by realizing that the numerator in this is the same as the numerator in this. Right? So P of A and B here, P of A and B here. However, if you divide that by P of B, you get P of A given B. If you divide it by P of A, you get P of B given A. So depending on whether you divide this number, same number, by P of A or P of B, determines what's on the left side and what's on the right side of this equality, of this probability. So Bayes' rule then uses the following trick. So it's kind of condensed form here, but imagine you multiplied both of these sides by P of B. You would still have equality. You would have P of A and B is equal to P of A given B times P of B, right there. And on this one, if you multiplied both sides by P of A, you would have P of A and B is equal to P of B given A times P of A. So the left-hand side of both of those that I just gave, those instances are different. However, the right-hand side is the same. The right-hand side of both cases of P of A and P of B, probability of both of them together. Since the right-hand side is the same, therefore the left-hand sides have to be the same. And so that's where this equality comes into play. You could imagine that in between this equality is P of A and B. So this is equal to P of A and B. And also this is equal to P of A and B. Therefore, these have to be the same. So it's a simple property, the simple fact that if X is equal to Y and Z is equal to Y, then X is equal to Z. So we have this equality. This is all based off of general rules of probability. And now Bayes' rule says, look, we can divide both sides by by either P of A or P of B. If we choose to divide both sides by P of B, then we have a conditional probability here, given P of A given B, in terms of P of B given A, P of A, and P of B. So this is Bayes' theorem. I'm not sure if you saw this in the previous lecture before, but this is Bayes' theorem. It says that the probability of A given B is equal to the probability of B given A times the probability of A by itself divided by the probability of B. So this is what Bayes, the Bayes classifier is going to do. If you can think of logistic regression previously, it was like using the left-hand side. It's like saying, what's the probability of a default? Great, so you saw this. What's the probability of a default given the information on the application? And logistic regression is trying to determine that probability, right? The Bayes classifier is going to say, don't use the left-hand side, use the right-hand side. So let's calculate. So if you can think conceptually, because so really I'm laying the groundwork, and then for the conceptual thinking, then the following will be much easier. Logistic regression is like saying, here's the information. B is the information about the applicant. What's the probability that they default? Bayes classifiers are going to say, okay, well, given that they default, what's the likelihood or probability of seeing this applicant? So conceptually, it's a flip of it. It's saying, here's my application. What's the probability that they default? That's logistic regression. Bayes classifier says, well, I'm going to pretend like you're going to default. I'm going to pretend that you'll default. Given that I pretend or assume that you're going to default, what's the likelihood of the information contained in your application? So in one way, it's like saying I'm evaluating, I'm a priori assuming that you will not pay your loan back. And then I'm evaluating whether your application looks like that or not. Whereas previously with logistic regression, I'm looking at your application and saying, what do I think about whether you're going to default or not? So it's flipping it. But then to be technically correct with Bayes classifiers, then you need an additional probability, which is the prior probability of your defaulting. Because remember, if A means you're going to default, and I assume that you're going to default to calculate this probability, I then also need to evaluate how appropriate is my assumption that you're going to default. That's what this prior probability gives. It says, I'm assuming you're going to default, and I'm calculating what is how much does your application look like all the other defaulters I know about, and then I'm multiplying by that by the prior kind of belief that you would default to begin with, right? I'm making an assumption about you that you're going to default and evaluating your application. I then need to scale that by how reasonable my assumption is to begin with without knowing anything about you. That's the prior probability. And then this is we don't have to actually worry about this. This is like a scaling normalizing constant that makes it equal. So you can see that this is the crux of the Bayes classifier, that we don't work with calculating this probability, which is what logistic regression did. We work with calculating these probabilities, which is what the Bayes classifier does. So we make assumptions and then evaluate an application based off of an assumption, and then scale that by how appropriate that assumption is to begin with. They both end up being the same exact thing. So you might think that, well, if this is logistic regression and we're doing a Bayes classifier here, then is logistic regression equivalent to the Bayes classifier? That's maybe a bit more technical than we can get into today, but the answer is no. Because these probabilities are in the most abstract, but when we talk about logistic regression, we're putting a form on this probability. We're making a definition for this probability that might not be true. Right? Logistic regression gives us a probability of a default given the application. But that probability, the way that we calculate that probability through the logistic regression function, is probably not true. I mean, it's not how things actually work. It's a modeling assumption. It's an approximation. With Bayes classifiers, we're also going to make approximations. We're going to approximate these two probabilities. And that's going to be assumptions as well. However, we're going to make different assumptions. So we're going to make approximations of how do we calculate probabilities of a person's application given that they're a bad loan or a good loan. That approximation is going to be different from the logistic regression approximation. So the way to think about it is that logistic regression is making approximations on the left-hand side. Bayes classifier is making approximations on the right-hand side. And those approximations aren't equal to each other. They're different approximations. Right? So perhaps the approximations that you can make on the right-hand side are more appropriate or better than the logistic regression approximation that you made on the left-hand side. And that's where you can hope to get improved performance. So we'll see that as we go on. So should we group our features in B? So that's where we're going, but yeah, that's what we're going to do. So what we're going to what we're going to do is we're going to take all the people who are in group A, who have a good loan, and we're going to group all their features together and calculate a probability on all of those together. And the same for the bad loans. Okay, so the big picture is we're using Bayes' rule, and then we're making approximations on the right-hand side. For our particular problem, A is whether they're a good loan or a bad loan. Another way of saying that is, do they default on their loan, meaning they're a bad loan, or do they not default, meaning they pay it back? And so that's a good loan. That's A here. So we need to approximate this probability from our data. That's the easy problem. The harder problem is approximating this probability, which is going to come later. But let's first focus on approximating this probability. So we're going to use our data to estimate this probability. What is the probability that somebody is a good loan or a bad loan? How could we do that? So the most obvious answer, and really kind of the default answer, using the word default in a different sense here, but the automatic answer, unless you have a good reason to do something else, is to just go to the data and say what fraction of the data was a good loan and what fraction was a bad loan. And that's how we're going to approximate this prior probability. So if we go to our data, we see this, that in our data set, about 14% were bad loans and about 86% were good loans. So we're going to use that number. The probability, my prior belief about whether you're a good loan or a bad loan is based off of this data set. Now, I should say, it's not in the notes, I don't think, but that assumes that the data that we collected is representative of the true data. You could imagine that that's not the case. For example, how could you imagine constructing the data set? You could say, I'm going to go to my data set. I have millions and millions of data points, and I want to construct a data set. And the way I'm going to do it is I want half of my data to be good loans, and I want half of my data to be bad loans. I'm going to collect a small data set or something like this. So I'm not going to maybe flesh out the story, but you could imagine that I'm artificially constructing a data set, and I make it so that half of my data set is good loans and half is bad loans. In that case, the data set would have 50-50, right? 0.5 for both. But that wouldn't necessarily represent the truth of reality because I made it that way. In reality, you would assume that most people are going to pay back their loans, but that information is not in the data because that's not how I constructed the data set. So in that case, you would need some other method for approximating this probability. For example, your prior knowledge. If you're an expert on a field and you kind of, you're a doctor and you kind of have a good sense of how often a person gets a certain illness, or you're in the financial world and you have a good sense of how often something happens, you could just use that expertise to manually define those probabilities to be more realistic than what your data set shows. So that's a warning that's very important, that the empirical fraction of the labels in your data set has to mimic the truth of your data in order for this probability to be realistic and to work in the future. So if we, one way we can avoid that problem is just collecting data totally at random, because then that's going to mimic reality, right? So we're going to assume that this was the case here, that we just generated the data totally at random. And so about 14% is bad loans, 86% are good loans. That gives us this probability. Then the second problem now is that we have to calculate this probability. The probability given you're a good loan of observing a certain feature, or the probability given you're a bad loan of observing a certain feature. And the way that we're going to do this first is we're going to focus just on one feature, which is whether or not their income is verified, and calculate that. So right now we're not looking at all the features, not all the covariates, but just one of them to make it simple. And we're only asking in the features whether their income is verified or not. So that's P of B given A. B is whether their income is verified or not. A is whether they defaulted on their loan or not. And that's how we can calculate P of B given A. So we do that and we get these numbers. That given somebody didn't pay back their loans, the probability that they verified their income was 0.36. Given that somebody, given they did default, given that they didn't default on their loans, the probability that their income was verified was 0.31. That's just from the data. Okay, so we've constructed a Bayes classifier. That's all we need. We have everything that we need to construct a Bayes classifier based off of the features that we're going to focus on. We can now use Bayes' theorem to calculate the probability that somebody defaults given their income is verified. And we're going to then make a decision based off of which one is larger. So we want to make a decision. Somebody comes in, they say that their income is verified. And based off of that information, you want to decide whether to give them the loan or not. So we're removing a lot of information in our data set, but just for simplicity, we're focusing on that one feature. So the first trick to notice in this Bayes classifier is that in both cases, you want to know, do I give them the loan or not? Is A positive or is it negative? You know, is A satisfied or is A not satisfied? Will they pay back their loan or won't they? A is what's changing, B is fixed, B is the feature. The thing to notice is that the denominator here is the same for both cases. So all we have to look at is the numerator and decide which one is larger. When A can be either to give them the loan, they're defaulting or not. So is the probability that they default greater than or less than the probability that they don't default? We only need to look at the numerator. We don't need the denominator. So that's a very useful feature of the Bayes classifier. So we do that. That's what this example is showing. We want to decide whether or not we give somebody a loan based off of their income being verified. So we calculate the two probabilities, the two values, one for whether they default, one for whether they don't default, and whichever one is greater, that one's more likely, and we make that decision. So when we calculate this for the default, we put in the probability that they default, and then we calculate the probability that their income is verified, that somebody's income is verified, given that they default. So it's a likelihood. What's the likelihood of seeing somebody's income verified, given that they default? Multiply those two together, and we get this number, 0.051. We do the same thing for evaluating that they don't default, that they pay back their loan. So we calculate the probability that they pay back their loan. Then we calculate the likelihood. What is the likelihood? What is the probability of somebody having their income verified given that they do pay back their loan? Multiply those two together, we get 0.269. So they don't sum to 1 because they haven't been normalized. But all we need to know is which one is greater. And in this case, the non-default is greater, which means that it's more probable that they pay back their loan than don't pay back their loan. So we would maybe decide to give them the loan if all we care about is which is more probable. Okay, so that's kind of the Bayes classifier in a nutshell. We can do the same thing. I should move forward. We can do the same thing for different features. So for example, what if they're source verified versus not source verified? And we can calculate those same numbers if we only want to focus on that. In all cases, it turns out that this is why this data set perhaps is not so interesting, but in all cases, it turns out that a person is more probable, more likely to pay back their loan than not. that's what the information in the data set shows. And that makes sense in general, that no matter how a person's application looks like, no matter what they look like, that if you have a data set of them receiving loans, people more often pay back their loan than not. However, you remember the threshold, which is coming later, that you don't necessarily make the decision based off of which is more probable. You might have a threshold. So it might be more probable that somebody pays back their loan than not. But if there's still too much risk of them not paying back their loan, you might decide not to give them the loan. And so that's where the threshold comes in. How much greater is it that they'll pay back their loan than not? Yes, so it's always more probable that somebody's going to pay back their loan. So if you needed to just make a prediction, then you're always going to predict that they're going to pay back their loan, because that's just kind of how life works. People more often than not, if they're asking for a loan, if they're just asking for a loan, more often than not, they're going to pay back their loan. But the issue comes in that you don't, like I said, you don't just want it 50-50. If somebody has like a 55% chance of paying back their loan, that's too much risk. So you might want to threshold it so that the probability has to be higher than a certain number. Okay, so let's now continue with the algorithm. So this is basically, I've already really taught it, but let's now review it again. Yeah, so that's also how you collect the data. I mean, you would hope that your data set's coming from real life examples. And so you're not going to see examples where people are not paying back their loans more, or even at a higher rate, at any significant rate, because the company, so to construct the data set to begin with, the company already did an evaluation. A company is already trying to give, so this is probably too much information about this specific data set, but you have to ask yourself, how did this data set come into being? The data set wasn't created by just randomly giving everybody any loan that they wanted. It was a real life example. So first, people had to want the loan, which means that they probably were motivated and they cared to pay it back. And also, the people giving the loans did some pre-screening, so they didn't just give anybody a loan. So the data set was constructed to be biased, kind of to try to be more towards having successful repayments. But as an aside, there is a story of a credit card in the 80s when they wanted to, Capital One, I think, was the bank in the 80s that wanted to get a good data set. So they actually did just randomly approve people and accepted the fact that they were going to lose money. But they wanted the data, they wanted the information, they wanted to know. I think it was Capital One giving credit cards, because maybe credit cards were fairly new at the time. They wanted to know what people were going to do, and so they would give credit cards to people being fairly confident that this is not a good idea, but they wanted the data so bad that they accepted the losses to get that information. So it was like almost an investment in getting the data. And then based off of that, they were able to, I'm assuming that this didn't last for long. They just got some quick data, and then they started, accepted some losses, and then they were able to better predict, and that helped quite a bit. So that's an interesting story that I remember hearing. But that's by now we have enough data. We don't need to do stuff like that. But you could imagine if you tried to break ground into a brand new, field, right? You tried to something really revolutionary. You would maybe do something similar. I know Amazon, for example, a lot of these companies, they take losses at the beginning. And I'm assuming part of that is because they need to do stuff to build up, their business. Okay. So now let's review again this Bayes classifier model. Let's recall that in logistic regression, the main quantity of interest is the probability of not defaulting. That's what we're calling A, what's the probability that they pay back their loan, that they don't default. We explicitly model this in logistic regression as a linear function of the input covariance transformed by this linear function, this logic function. The naive Bayes classifier tries to estimate the same probability from a different perspective using Bayes' theorem. So instead of calculating the probability that they don't default, given the input, we're going to try to estimate the probability of the input given that they don't default, given that they pay back their loan, times a prior assumption about what's the likelihood that somebody pays back their loan, divided by this normalization constant, which actually turns out not to be so crucial. We then, so we work with the right-hand side. That's the key insight of the Bayes classifier. We then make our classification decision based off of whether or not this right-hand side is above a certain threshold. So now we have to know, how do we learn these two distributions? So we already kind of saw this before, but again, I think we're reviewing here. So for this classifier, a client with given covariates is classified as a non-defaulter if this is greater than this, or technically if this is, if this divided by this is greater than a threshold. We have 3 different values now that we need, or I guess 3 different values here that we need to worry about, 3 different probabilities. First is the probability that they default or not default. So one of these is 1 minus the other. So this is 1 minus this. So we really just need one number. These are the probabilities that somebody defaults on their loan a priori. So this is something that we can estimate from the data. I already went through this. This is just the probability that we estimate in some way. It's a prior probability without knowing anything about a person. A priori, we want to know what is the likelihood that just anybody is going to default. How common is it? The second value is this normalizing constant, which I won't read this. It's actually not necessary. We don't have to worry about this because all that matters is the numerator. The covariates are the features. So you can think of the covariates as the information that you have to base your judgment off of. So it's, person fills out the application, they tell you their income, they tell you all this information. Those are the covariates. They're also called features. Covariates is a statistical term from the statistics world. Features are used by machine learning, data science, but they mean exactly the same thing. The third is the key thing, the key value that matters, and this will change for each problem. So this is the same for, no matter what the problem is. If there are two outcomes, this is kind of the same thing each time. It's just calculated based off the data. This distribution, the probability of the covariates or the features, given the outcome, is going to change depending on what those features are. So if your features are real values, then you might pick Gaussians. If your features are binary values, you might pick Bernoulli distributions, discrete distributions. We're going to see in our case that it's mixed. Some values are real values, some values are categorical valued. So our distribution is going to be a combination of, in our case, Gaussians and non-Gaussians. So we can estimate these by looking, but at the end of the day, what you get is you divide your data into all the people who paid back their loans and all the people who didn't pay back their loans. And then you learn 2 separate distributions on the features based off of which group you're looking at. All right, so I'll keep moving forward. So there's a conceptual issue that comes into play, though. If you have high dimensional data, sometimes it's hard to learn fully a distribution on that data that has full covariance. So for example, think of it this way. If your feature vector is a binary vector, of length 10, then there are 2 to the 10 different things you could observe. And it's hard to learn a distribution, a discrete distribution on 2 to the 10 values, because you need a lot of data. And it gets even worse as the cursive dimensionality holds. So the naive part, why this classifier is called naive, a naive-based classifier, is we're going to make one additional assumption that's crucial that makes it very easy to learn. We've seen that we want to calculate the probability of the entire feature vector. So this might be 10 different values given the result of their loan status, default or not. However, this distribution could be high dimensional, and the higher dimensions that you have, the more data that you need to approximate it well. So the reason is because if you have many dimensions in your covariates, your higher dimensional distribution is trying to learn all combinations of covariance. It's trying to learn how correlated all these different dimensions are. And you need more data to learn those correlations. So what we're going to assume, again, because we get to decide this distribution, we can choose what this distribution is. We're going to make a simplifying assumption that all of the information, all of the features are independent of each other, given the status. So we're going to pick a distribution. This is a multivariate distribution on multiple dimensions. The form of the distribution is going to be factorized, where we can calculate different distributions for each dimension separately. And then the final distribution is the multiplication of all of those distributions. So the naivety, so that's why it's called naive, and that's the assumption. You know, naive means that you should know better, right? So it's like kind of putting you down, but it means that you should know better. You know this isn't true, but you're pretending like you're a simpler person than you are, right? So we're making assumption that all of these features are independent of each other, given which category they belong to, good loans or bad loans. We know that that's not true. We know that there are correlations in our data, but we're going to make this assumption because it makes it much easier to learn these distributions. We don't have to learn high dimensional distributions that are complicated. We can learn very simple distributions on each dimension separately and then multiply them together. Furthermore, it's very nice because in our data, some are real valued numbers, some are binary, some are multi, have multiple values. Defining a distribution on that in high dimensional space is very complicated, but if you can define separate distributions, it gets very easy. You can define a Gaussian for the real value discrete values. You can define a binomial or a multinomial for the discrete values, and it's very simple. Okay, so I'm really falling behind, so I'm gonna speed up. So in this exercise 3, I think really what we're doing is we're building up to the final model. In exercise 3, what we're showing is now what happens if we look at more than one feature. We look at the term of the loan and the verification status. And we want to calculate the probability of both of those things together, given whether they're a good loan or a bad loan. So now what we would end up doing here, and that's what this is showing, is we calculate the probability of the term of the loan, whether it's 3 years or 5 years, given a default. And separately, we calculate the probability of a verification status, given it's a default. And then we multiply the two together. And we have now 2 cases. It's either default or not default. That's what this table is showing. Among all the defaulters, the probability of not being verified and having a 36-month loan is this, and so on. Right? So these are the multiplications. These are the 6 different combinations that you can get among the defaulters. These are the 6 different combinations you can get among the non-defaulters. And so this is the likelihood term. of the Bayes classifier. Now let's imagine that a client whose income has been verified asks for a loan for a 5-year payment plan. Should we give them the loan or not? So first we have to take this number, this is the likelihood, and multiply it by the prior probability that they default. And then we have to take this number and multiply it by the prior probability that they don't default. And you get these two numbers. We can then go to the corresponding entry in both cases. So it's been verified. So I think we're interested in this entry, and they want 60 months. So this is the number for the default, and this is the number for the non-default. And we see in this case, not defaulting is greater than defaulting, so it's higher probability, so we might give them the loan. That's where these two numbers are coming from. So now we have to wonder what happens if instead we use a threshold of t equals 0.8. I think I can skip this part, but the important part here is that we don't have to give the loan based off of which is bigger, but we can calculate the threshold and do it based off of that. Of course, in order to do that, we need to divide by the probability of the covariates to get a final probability. So at the end of the day, you normalize all of this to get a probability. You have to scale all of this to turn it into a probability. And then you can calculate the threshold of what probability they have to be above before you give them the loan. We do that, we calculate the ROC curve, and we see that the performance, so this is the logistic regression baseline, this is random guessing. We see the performance has decreased, so that's not good. However, remember that we're not looking at all of the features in this example. We're only looking at the term of the loan and the verification status of the applicant, and we're throwing away other information. So of course, you would expect the performance to take a serious hit if you're not looking at all that information, and indeed that's what happens. You get worse performance, but still better than random guessing. Okay, so now let's look at, those are the discrete examples. Now let's look at the continuous covariates. What this exercise is showing is that we can now consider incorporating continuous values as well. And to do that, rather than calculating discrete distributions, we're going to learn Gaussian distributions. That's what this information is showing. I have a half hour and I still want to go through the outline of the decision tree. So basically, there's a lot of data analysis going on here. I believe you've seen all these plots anyway. So you can see violin plots of what is the distribution of the loan amount that they're asking for, depending on whether they're a defaulter or not a defaulter. So you see these two distributions here. You can do the same thing for the annual income here. You see there's a huge tail because some people have huge incomes that skew the violin plot. If you look at the feature of the interest rate, you see that the people who fully pay off their loan, in general, tend to have lower interest rates. So that's informative. Whereas the people who don't pay their loans, the interest rate tends to be higher. That makes a lot of sense because they're trying to keep up with the interest. However, when we pick the distributions for each of these features, if we're going to pick a Gaussian, we need the data to be Gaussian, right? So the violin plot here, tells you that learning a Gaussian on these two distributions will not be a good idea because there's a very heavy tail. But if we take the log of the annual income, right? So this is the log of the income rather than the actual income. Suddenly the data looks very Gaussian, right? So there's a slight difference. The people who pay their loans have a slightly higher log income, but it's not too noticeable. But learning a Gaussian for this data and a Gaussian for this data is clearly much more meaningful. Additionally, if we look at the loan amount, this doesn't look very Gaussian, right? So this is the feature. We have to learn a distribution on this data for the bad loans and a separate distribution on this data for the good loans. If we pick a Gaussian, this doesn't look too Gaussian to me. So that might be an inappropriate distribution. So there are two options. You could pick a different distribution, or you could perform a function on these two data, on the data, to try to make it look more Gaussian. So that's what we're going to do here. So if we took the square root of the loan amount and plotted the violin plot there, suddenly now it looks a little bit more Gaussian. And so we're going to learn a distribution on the square root of the loan amount. So we're performing functions of features to calculate our before we calculate our distributions, because for continuous features, we want to use a Gaussian distribution. And so we need to make the data look Gaussian. Okay, and so now we implement it. This is something that we can skip through. We implement the distribution on just the continuous features, and we get some improvement in performance over just the discrete features, but we haven't yet looked at everything together. So the ROC curve is still a little bit worse for the naive Bayes classifier than it is for the logistic regression, which is the red line, which uses all of the data to learn the classifier. Okay, so all of this is code to now finally do the final thing, where we're going to train the classifier using, train the naive Bayes classifier using cross-validation on all of the features. That's what this is. So really, I know I'm skipping through a lot, but this is just building up the same ideas, doing more and more, right? So this is the final plot that you get when you do tenfold cross-validation, which we talked about before, learning a logistic regression classifier and a naive Bayes classifier on all of the features in the data set. Right, so this is using all of the information in the data for both classifiers. And unfortunately, there's no huge aha takeaway, because the performance is essentially the same, right? We see logistic regression and naive Bayes have almost the same cross-validated performance. The uncertainty is roughly the same. Both are better than random guessing, but they perform roughly the same, meaning that whichever you pick, they're both kind of equally good, which makes sense, I think, for this data set because it's fairly simple. But my final point before we move on to the decision trees for the last half hour is that the naive Bayes classifier in this example, the conditional distribution on the features, on the covariates, given the loan result, either they paid it back or they didn't, uses all of the features. And some of those are real valued, and some of those are discrete. For the real valued, it's naive, meaning that we calculate separate distributions on each of those features. For the continuous ones, we learned a single Gaussian. And for the discrete ones, we learned a multinomial distribution based off of the data in each group separately. Then to get the final probability of the entire feature vector given the class of the point, we took each of those distributions, evaluated them on their separate features, and then multiplied it all together to get one number. That's the final probability that we use. Okay, so that's the naive Bayes classifier. Let's now move on to the decision trees, which is fairly intuitive. So actually, I think it's something that we can kind of grasp pretty straightforward. So the decision tree classifier makes a decision of what class your data belongs to by starting at the root node of a tree and then moving down that tree until you hit the bottom. And at each point, the decision of whether you go left or right down the tree is determined based off of some information in your data point that you want to classify. So these are the same things depending on whether you can see it or not. So here's an example from this data set. There's a lot of information here that we're going to see in a minute. So we haven't talked about what is in each of these pictures. But the big idea is that you start at the top of, you have a data point that you want to classify. And you start at the top of the tree and you ask a question about that data point. And if the question that you ask is true, you go left. If it's not true, you go right. So for example, in this example, the question that we ask is, did the person want more or less than $15,000 in their loan? So specifically, is the person requesting less than $15,000 in their loan? If the answer is yes, you move left. If the answer is no, they want more than that, you go right. Notice now, depending on whether you go left or right, you have a new question. If you go left, this is your new question. So you can ignore the bottom four and just look at the first one. The new question is, okay, are they asking for less than $2,900? Answer is yes, go left. Answer is no, go right. Notice that you're only going to get here depending on your result of the first question. So in your first question, if the answer was no, you go right. Then the new question becomes, okay, are they asking for less than $30,000? Yes, go left. No, go right. So you're only going to ask that question if you get here, right? So you're not going to ask every single question for each data point. It's going to start at the top and then move left or right depending on a specific question, and then you get a new question. Right? Eventually, you're going to hit the bottom of the tree. And then what happens is the bottom of the tree, there are no questions. The bottom of the tree tells you, okay, here's my prediction. So if you end, this is not so exciting here, but if you end at any one of these nodes in the tree, the blue nodes, you're going to say, I think you're going to pay back your loan. If you end up at this orange node, it's going to say, I think you're going to charge off. Unfortunately, it looks like no data ended up here in the training data. So, but that's the big picture of what a decision tree looks like. You have, it's a binary tree, meaning that at every single point you go left or right, one of two directions, depending on the answer to a question. And you keep moving down and asking new questions and then going left and right. Eventually you hit what's called the leaf node, which means that there are no more questions, you can't go down anymore. And wherever the data point terminates, the leaf says, here's my prediction. It gets like a prediction for all the data points that end up here, have a certain prediction, and also a confidence. So like how confident is your prediction? That information is contained in here as well. So that's the decision tree in a nutshell. That's what it looks like. Of course, now the problem is, how do you learn this decision tree based off of your data? Right? We have data, and we now need to decide what are the questions that we ask in each of these nodes in the tree. So this tree says the first question that you ask is whether the loan amount is less than $15,000. That's the first question you should ask. But how do you know that that's the first question, right? So that's what the process of learning the tree is meant to do. It's meant to decide what is the first question that you should ask, and then what are the other questions that you should ask. So I'll get to Jeannie in 1 second. So when you have many categories in the variable, you mean if there are many covariates. So here, yeah, notice that I think I answered your question. So there's only loan amount here. In our problem, we have many different features. And so in the tree, the way the tree works is it's going to focus on one feature for each question, but maybe the first question asks about loan amount. And then the second question asks about what's the interest rate, or what is your income? That all has to be determined by the algorithm. The algorithm is going to determine what are the questions you ask. And sometimes you ask questions about the loan amount. Sometimes you ask questions about the interest rate. Sometimes you ask questions about other things in your data. If it's a categorical, what that would end up looking like would be, so for example, categorical is 36 or 60 months, for example. The question could be, are you asking for a 36-month loan? Go left if yes, go right if no. If it's multiple, like verification status, which has 3 different options, what the algorithm would most likely do is group those in some way. It would say, are you verified? Go left if yes, if not, go right. And then if not, that means you're one of the other 2, but I don't know which. So it's just a simple binary question. However you can make the binary question, that's what it is. Is this true or not? Are you verified or not? Are you self-verified or not? But what the question is that you ask, you have to then determine from the data running the algorithm. Okay, so how does this algorithm now work? So in this example, we're going to create a decision tree that predicts loan status, good or bad loan, based off of these 2 features, the term of the loan and the feature verification status. So notice that we're choosing to be a binary, discrete variables. This is binary, this is categorical. Is there a way to artificially increase the weight? So off the top of my head, I'm not sure. I would have to think carefully, but yeah, that would be a next step question. I would assume that there's always if you know some feature is much more important than another, hopefully the decision tree will notice that. But if not, you can do that. But I'm not going to be able to go into detail about that. What does the value vector mean? I don't see that one. Okay, sorry, I should move ahead. I have 18 minutes to finish this. Okay, so what we're going to do is, because it's binary, the reason we pick discrete first is we can look at all the combinations. We're at the first node in the tree, and we need to decide which feature to look at. Do we look at the term of the loan and make a decision based off that? Or do we look at the verification status and make a decision based off that? And because there are a finite and small number of options that we can make decisions, we can just enumerate all the options. For example, we can focus on the loan status and see all the clients, break the clients apart based off of whether there's 36th month or not, and then look at what fraction of them made their payments or not. So here, I believe, did they ask, this is a binary, are they 36 month or not? So all of these people, if I get it correct, did not ask for a 36-month loan. That means they asked for 60 months, right? So these are all the people who asked for a 60-month loan. These are all the people who asked for a 36-month loan. Then this column tells you the number of those people who did not pay their loan back and the number of the people who did. So there were 2,367 people who asked for 60-month loans and did not pay their loan back. There are this many people who asked for 60-month loans and did pay their loan back. And here, these are the number of people who asked for 36-month loans and did not pay their loan back. This is the number of people who asked for 36-month loans and did pay their loan back. So you can see here that if you just focus on that the fraction of people who paid their loan back with 60-month loans is 0.77. The fraction of people who paid their loan back with 36-month loans is 0.89. So now we can say, well, what if I made my decision, my first decision, based off of whether they're 36-month loan or not? How good would that decision be? Well, we have to look at, so this is where the Gini index comes into play. It's a measure of how good your result would be if you had made your decision based only on that criteria. So the Gini index looks like this. It's the probability of, so we're saying, if I made my decision based off of whether it's a 36-month loan or 60-month loan, I'm going to get two groups. I'm going to get a group of all the people who are 36-month loans who go one direction, and I'll get a group of all the people who are 60-month loans that go the other direction in the tree. Now that I've split my data into those two groups, imagine I wanted to classify based off of those two separate groups. How good is my classification? Well, you look at the probability of those two separate groups of the two different classes. So, and you calculate a value of how well that probability is. So the Gini index is one way of calculating the measure of how confident you are in your prediction. It's simply the probability of one thing, of one class, times 1 minus the probability of that class. So the probability you pay your loan back times the probability you don't pay your loan back. Then you throw a 2 in there. This would be the Gini term for all the people who are who go down the 36-month direction of the tree. The Gini term for all the people who go down the 60-month direction of the tree have this number, because this is their purity. Notice this is a number that you want to be as small as possible, because the closer you get to 1 in one of these terms, the closer the product goes down to 0. The closer you get to 0.5, which is most uncertainty, the closer it goes up to, in this case, 0.5. The reason you want this Gini to be small is because it tells you that all of the data that filtered into a certain group all have the same, mostly the same labels, right? Whereas, and so on. And likewise with the other group. Ultimately, you want to create a tree so that when you filter your data across these trees, all the data that ends up in each node of the tree, in each leaf, the tree at the bottom, all agree with each other on what their label should be. That there's as little disagreement as possible. The Gini index is one way for calculating that measure of agreement. I should say that this Gini index, it's used to learn the algorithm, right? That's what we're talking about. Now, how do you make a decision about how to learn this algorithm? Well, you have to look at all the ways you can decide. At the end of the day, that it's a very computationally intensive algorithm that the computer, fortunately, is going to do. It's going to look at all of the possible decisions that you can make, and for each one, it's going to calculate the resulting Gini index of that. And then you're going to pick the one that gives you the lowest Gini index. It's a greedy algorithm in that sense, that you want to pick, you want to create a decision that makes you as confident as possible about your decision, about the result as possible. So that's what this math is doing. This is everything in this part is what the algorithm is doing when you call a function. So we can perhaps skip over that. But at the end, you get decisions that come out of it. So the way that the algorithm is learned is you start at the bottom, at the top of the tree. You then decide, how do I make my decision here? And then you get your result. You then move down the tree and continue to break this tree up. So the first step in the algorithm is learn a tree that only has 2 leaves. It's 1 node and then 2 leaves. And what is the best tree that I could get from that? The next step in the algorithm says, okay, I'm going to take each of these 2 leaves and break them up. I'm going to turn this leaf into a node and then break it into 2 more leaves. And I'm going to do the same thing here. One second with your question. And then the result is, it says each one, what is the resulting leaf? So the question, does the algorithm consider every possible split at each iteration? So yes, it does. It's brute force. Maybe there are some advances that have been made to make it a bit more efficient, but the way you should think of it is that essentially, yes, it's considering everything as we're speaking about it now. However, the way that it does it is by only looking at the data that has filtered to a certain leaf. So at the top node, you have your entire data set. You then break that into two groups, all the data that goes this direction and all the data that goes this direction according to this algorithm. The next step then in the algorithm is it says, okay, for all the data that went in this direction and only that data, I want to break that up into two groups. And I need to decide how to do that. So it looks at every possible split in order to do that, but it only uses the data in this group to decide that split. And then it makes a split. And the same here, it only uses the data in this group to decide how to split it. So you can immediately see that as your tree gets deeper and deeper, you're going to have less and less data to base your splits on. And so you can't make your tree too deep unless you have a ton of data. And that's all part of the learning process of the algorithm, that if you're using, good code, a good algorithm, it can automatically take care of all these issues for you. But that's an issue you have to be aware of, that as you keep breaking your data into smaller groups, you're going to have less information to make further splits. Okay, so that's the high level idea. It's very easy to overfit. That's one of the big drawbacks of a decision tree. It's very easy to overfit your data. You can keep splitting and making the tree bigger and bigger and doing perfectly on your training data, but then do poorly on your testing data. So the way that you can account for that or fix that is all, at this point, it's complicated. It's built into the function though, to help try to learn trees that don't have this overfitting issue. So I think I can skip through this stuff. At the end, what you end up getting is a partitioning of your space. So this is just if you have two real valued features. Is the difference between the two genies significant? So sorry, in this case, yeah, I kind of glossed over that. You get two genie terms here. You have to actually combine them into one final genie term for that particular split. And so this term here is only looking at the genie for one split, one decision. You then calculate that genie for every possible decision that you can make. And then you pick the smallest one. And most likely there will be a few different options that you can choose when you decide how to determine this split here. There are multiple options you can choose that all would perform roughly similar, but the rule is that you pick the best one, because that's called a greedy algorithm. You're just trying to always do the absolute best. So you end up partitioning your space like then to something that looks like this. So in the final 7 minutes, let's talk about how, we talked at the high level about what a decision tree looks like. What is a random forest? So a decision tree has an issue of overfitting your data that's very serious, that can really hurt your performance on future data. What a random forest does, it's pretty straightforward to talk about at a high level. A random forest is going to learn many different trees on your data set. And so say it'll learn 1,000 different trees on the same data set. And then each tree is going to make a decision for a particular data point. And the final decision will be the combination of those decisions. So rather than learn one tree, one decision tree on your data, it's going to learn 1,000 or something like that on your data. But the issue is that if you have a tree learning algorithm and you feed your data into that algorithm and it's a greedy algorithm, it should give you the same tree each time. So how do you get different trees? How do you get different views of your data? So that's what the random forest does. It uses something called bootstrapping of your data set, which is, I don't know if you've seen bootstrapping, but it's a statistical technique. And it modifies how it makes the decisions how to split. So it doesn't, like somebody asked, look at every single possible decision and then pick the best one. It randomly subsamples a set of possible decisions and then picks the best one only on that random subset that it checks. So the big takeaway is that each tree that you learn on your data set is viewing the data from a different perspective. It's not seeing exactly the same data set, and it's not looking at every single possible decision as it grows the tree. It's looking at random variations on your data set, random permutations. So it's kind of the same data, but randomized a little bit. And it's also randomly choosing how to make its decisions to split the tree up. So the tree that you get, any individual tree that you get, will therefore be a little bit worse than the original tree, the best possible tree. It'll be a little bit worse because you're not learning it on, all the information you have. But the combination of these trees, and this is why it's a powerful technique, the combination of these trees will be better than the original tree. So each tree is a little bit worse than learning the best possible tree. But when you combine all of their votes, the result is improved. So in the last 4 minutes, we run this, and I'm sorry, I should skip ahead. We get the final performance. It looks like this, where we have our random guessing, we have our logistic regression, our naive Bayes, and our random forest. We do the cross-validation on the random forest as usual. So how do you choose the number of trees in the forest? So that's, technically you can choose as many as you want. There's not an overfitting problem with this, which is one of the reasons why it's so powerful. So usually what you do is you keep generating more and more trees, and then watch the performance as you get more trees, and eventually the performance will stop improving, and then you can stop. But in general, the number of trees is a large number. It's hundreds or thousands of trees. So we do that for all of these algorithms. Unfortunately, it's not an exciting takeaway because performance is all the same. It's a fairly simple data set. However, the uncertainty in the cross-validation with naive Bayes is slightly smaller. So you could make an argument that naive Bayes is better because there's less uncertainty in how your performance will generalize to new data. Is it possible to make a tree without modeling? I mean, just with the original data it had. So the modeling of the tree means that you have to decide what the tree is. So you can make a tree based off of your own knowledge. But what this is trying to do is say, use the information in the data to decide what is the best tree. So there's, not sure if that's the question, but here the modeling in this part is how do you use the data to decide what the tree should look like, which is something that you could know in advance. I mean, if it's a problem you're an expert on, you could make a tree out of your own head, and people have done that before. But in principle, you would hope that the data would have, the algorithm would be able to find something even better than you might think. Okay, so I should wrap up in the last minute. So when deciding which model to use, the gold standard is always to look at prediction performance on a held out data set. So for example, something like the AUC. There are many factors that you should consider when choosing between models. First is the purpose of the analysis. Second is the number of data points. So the more data you have, the more complicated the model you can choose. And third is the number of covariates. The higher the dimensionality of your data, the usually the more data you need, and you need to make some decisions like a naive Bayes classifier. In our data set, we were looking at about 40,000 samples and only 9 features. So each data point had 9 bits of information. And we had 40,000 data points. So it's a lot of data and not many features, which is why all of these different models tended to perform the same, because it's a lot of information. But if the dimensionality of the data increased a lot, then you might need to consider other models. So I think I'll end there, because I'm sure everybody needs to take their break. But the final takeaway is that you have many different classifier options. Each one kind of requires you to learn a new technique. Each classifier is a brand new thing. They all have their own advantages and disadvantages, but ultimately they're being used for the same problem, which is to make a decision of what the class label should be for an input data point. Okay, so I think the schedule says that we have a 20-minute break.
Yes, John, that's correct. So we are gonna go into a little break of 20 minutes and we'll see you at 10:20. So go have a rest, drink some water, and we'll be back soon.